Welcome back. Nice brisk morning. What I want to do today is continue on where we left off last week, which is looking at the sparse triangular solve. And, whoops, there we go. So it's this algorithm here that we're implementing. And so the recursive version of this is fairly straightforward. For the non-recursive version, we have to do our own stack. Okay, so think about how you would write this non-recursively. So we need our own stack, and so you've got this DFS function. It's going to be non-recursive, but it is going to start at a particular node j, because it's been kind of called non-recursively here. So there's a node here that we start at, and it's going to be unmarked, so we mark it, and then you're going to start this loop. Now, if you need to do a recursive call here, when you finish the recursive call, you want to pick up this loop where it left off, right? You can't start it over again, obviously. So if you think about how this recursion is going to be working, at the very top level, it's going to find a case at which it needs to iterate. It's going to be on a very top node with a collection with an adjacency list I, and so those 5 little lines there represent that adjacency list. Okay, and so it's going to be constructing what's called a DFS tree. DFS tree is where who calls who, basically. And so you start here, and then you start another DFS. And when you come back, so there's all these iterations that are in partial state of completion. So at any given time, like here, for instance, we might be at this point in this iteration of this loop, at this point in this iteration of this loop, and at this point in here. Okay. So when we finish these and come back, so you come to the end of this loop, you're going to have to come back and say, well, I don't want to do this one again. I just did it. So we've got to pick up where you left off and increment this state of the position where you were in that loop, right? And so at each level of recursion, we need 2 things. We need to know where we are. What node is it we're talking about? Like right here, I need to know that, well, this is the parent, say j, for example, that I'm at. I'm at the loop for j. I'm going across this node. And I need to keep track of where I am in the sequence, where I am in that iteration. Well, to do that, the most natural way to do that is to store the value p. All right, if you think about what happens in the recursive code here, I wrote this intentionally very tersely to illustrate several things. First of all, what happens when you do a recursive call, right, is you have to push your parameters on the stack and then do the call the function and then pop them back and so forth. Well, these things on the stack, the W here, is really a constant pointer. It's obviously the contents are not constant, but the pointer could be thought of as a global variable. Same thing with the XI, which is the thing I'm using as the output stack. Top is being modified, however, but if you will, that's a global variable. All the recursions are going to see that same value of top. So all these variables here, even L and L itself, can all be treated as global variables, if you will. So I could have declared this. In fact, I did as I was developing the recursive version. I pruned away all these parameters, and I just had j left, and what else did I need? I think that was for the recursive version. Okay, I pruned all these away. I needed j, and I just declared these as global up top, just to make sure my thinking was right. Sometimes you write code that you're not going to distribute, but you just want to make sure, okay, is this idea correct? So then we're left with 2 things. J, which is going to change at each level of the recursion, and P. It's a local variable that would have to go on the call return stack if you wrote the compiler to compile this code, right? So there's two things, P and J, we've got to keep track of. And so so I'll see how we do that here. We're going to have to pick up and have we're going to have a place to stack J and a place to stack P. Now, the interesting thing about J, so I could do the following. Okay, I have already this output stack here, so I'll call it script I, where I just stuff all the results when I'm done. So there's a push here. I already have that stack. Okay, so then I could create another stack here, and I would put on here two integers. I would put on here the J node that I'm at, and the value P, which is this integer index, which is looping through that column. Okay. So I've got J and P on a stack, and then to do a recursive call, then I would have to push the current context onto this stack, the current J and P, and then start the one with the new recursive call on this value for J. So here's my new value for J. So J would change to this, and then P would change to the column pointer for that column. Okay. Well, one thing is very useful to observe is I can cut the memory space for this stack in half. And the reason we can do that is because think about what it is you're pushing this onto this stack. You're putting row and column indices. In particular, well, you can think of them as column indices. Every time you see an xj that's non-zero, that means it's a column j that's reflecting. And so there's column indices going on here. But the only thing that happens on these on the column indices, well, better yet to think of as just node numbers. Okay. When you're at this node, you do this work, and then when you're done with this node, then it goes on the stack. So any given node is either not being touched at all, in which case it doesn't appear in either place, either the output stack or the recursion stack, or it's in progress, which means it's on the recursion stack, but then it wouldn't be on the output stack. So a particular column index J, a particular node number, if it's here, it won't be here. And then the only time it goes in the output stack is when it's finished. In that case, we pop it off this recursive stack. You see, it's right here that when J finishes, it's the finished work, okay, that sticks J on the output stack. So J is only going to live in one of two places at most. It's only going to be in one place, either the recursion stack or the output stack. So I use a very common trick. Then I only have to have the stack for P, and I'll have to have a head pointer to keep track of where I am in this stack. But the stack for J can be put here on top, because you've got this memory space of size n, and any given column index is either here or not at all. So no matter what happens, you're going to have some empty space in between these two competing stacks. In other words, you've got a memory space that stacks can go in either direction towards each other. And I can assert that they'll never collide. Do you see that? I have two stacks, one for the output, one for recursion. Any given node will be node number will either be here or not at all. So if all the nodes are there, well then this memory space is full, but that's fine. So they don't collide. The stacks cannot have, I cannot have n plus 1 nodes. I have only n nodes, and I've got n space. The boundaries will shift, okay, but at any given time they'll never overlap. Right? You look puzzled. Do you follow? So no, you don't follow. You're not puzzled. What's that?
I don't follow
this discussion here.
This stack particularly.
This stack.
Yeah. How you're merging the two into one stack.
Well, I'm not merging the two. I'm just not putting J there at all. So this stack, the recursion stack, is held really in two places. There's two integers I have to store. One I have to store in its own stack because I don't have space for it. But the other integer I can put here. So that's why. So it has to be split, just because of, the width of this is just one integer, because that's the output. And so I need really. I could have used a single memory space of width 2n, but then I guess that's what I'm doing anyway. Actually, I've got 2n memory space. I could have thought of it that way. Yeah, well, I could draw it that way. How about if I do it this way? That's not a bad idea. Imagine if I have a memory space that looks like this, and it's of size 2n. And so I can hold at any given point on the stack, I can hold two integers. So this is another way of looking at it, actually. And so here we have a stack that's growing that contains the output, the J. But I only need to store it in one half of that space. And here I have another stack. It's upside down. So when I push this, a push goes and puts stuff here. Okay, and a pop removes it. And here I put the node numbers of the nodes that are in action. They're nodes at which I'm not yet finished with. And with each node that's not finished, I have to store the index of this loop, and they're all going to be different. I have to store the index in the loop at which that node is, right here. So, and then these two stacks can't collide, because if I either got a node, any given node will either be here, or it'll be here, or it'll be out here, nowhere. It won't be touched, one or the other. So is that maybe more clear? Yeah, and so now the observation is, well, I'll just split this apart, and that's what I've got here. And one's reversed, one's flipped from the other. So, but the code looks like this. But if you want to think about it like this over here, this is maybe simpler. And if you want to do even further, you can say, well, let's just really what all I've done is I've, in a sense, sliced this, turned this on its head. Okay. And I've got the call return stack here. Each record in this call return stack is the node number and the index P. And pushes and pops and just pushes here. And now I've got these two independent stacks. And then the observation is, the final observation is, well, wait a minute. The sum total of the space of the two stacks is never, the sum total sizes of the two stacks is never larger than n. So I can take this and go flip, put it here, and then they will never collide. So they can share the same space. The worst case, though, is that any one of these stacks will be of size n at some moment in time. I mean, it's possible, for instance, for the output to be completely non-zero. You could traverse the whole graph in the graph traversal. The reach could be all the nodes. So the output stack will be full. So there's no space left for the recursion stack. Well, but see, it'll only be full when you're done with the whole algorithm, in which case all the recursion is finished. So so at any given moment, that you could have a case too where the DFS starts and then it starts the next node and starts the next node and starts. Like have all the nodes started and none finished. So the recursion stack would be full, but you see if the recursion stack is full, nobody's finished, so nobody's in the output stack. So the spaces can be shared. So that is the sum total then of this algorithm, and it's right here. So that's, well, there's one extra little twist that I have to worry about. And that is, and there's, right at the moment, there's no reason for this, but I have a permutation in here as well. It gets even gnarlier than what I've described. I have a column permutation, and so the idea is that this column permutation here, if it's null, then it's treated as just identity. So for a moment, just think of it as identity, and then we can ignore it. But the J nu, so remember the inverse permutation function goes like this. P inverse from old to new. Okay. And what's going to happen later is that the actual location in the graph, I still want to think of this as node J. I want to call it node J. But its actual location in the data structure will be different than the jth column. If you want to think of it that way, that's a convenient way to think about it right now. And so this J nu could be different from J right here. And there's another twist that this permutation could be partial. It could be the case that in fact I don't yet have a complete matrix yet. Okay, and what happens here is implicitly I have an identity. I have ones on the diagonal, but they're not actually there in the data structure yet. The whole reason for this is I'm actually going to be using this algorithm as part of the LU factorization. It's going to compute L on the fly. But it's going to have to do triangular solves on this L as we go. And so L is not yet constructed yet. And to denote the place that, oh, it's not yet there, then the P inverse permutation is not yet completed. And so there's a -1 that comes out of here. Nu is -1, which is empty, in other words. So if you put in a column here and you get out empty, that means that you're here somewhere. But if you're here, there's no edges to traverse. And so we can declare that, in fact, we can't look, if J nu is -1, we can't look at column -1. It doesn't exist. And so this algorithm skips that, and it says go from 0 to 0 or go, iterate from nothing to nothing, and so no work gets done. So it's a way of trimming off that spot there. Okay. So for the moment, though, let's treat J and J nu as equivalent. Okay, so just pass in, think of P inverse as null. And then, so then J nu will never be negative. That's kind of odd. What does it mean to have a negative column index? So here's the algorithm. And so what it does, it's non-recursive. You're passing in, I have a stack for the P pointer. So I'll call this P stack over here. And I call this xi. And the P stack, actually, I turn it upside down as well. Because see, I've turned, in fact, it's probably better to look at this picture over here. Actually, this is maybe a more, thank you for asking that question, because this is actually a more coherent picture, literally. I've got the array xi that holds this half of the stack. And I've got the array P stack, which holds this half of the stack. It's just that I don't need it for this piece there. That's empty, it's unused space. And of course, this is all unused. This is in use for the output. And then this is in use up here. And so the head pointer for this part starts out as 0. The head pointer will always point to the next unoccupied position of the stack. So there's a head pointer. I call it right here, head. For this, for the recursive stack, I use the word head for the pointer of that stack. And for the output, I call it top. And top always points to the actual entry there. And so it's initialized to n. So top is initialized to n, and head is initialized to, now wait a minute. No, I'm sorry, I lied. Head is initialized to 0. Yeah, the stack pointers always point to the entry at the top of the stack. There we go. So we've got a head pointer here and a top pointer here. The word top is used there, and the word head, the variable head, is used for this position. So this is what I'm going to do the recursion on. And so let's look at this algorithm then. The very first thing I do is I need to put onto the recursive stack the starting node, j. And so that's akin to this. I'll put a j here. But this slot here is for the moment is left empty because I'm not yet finished with this iteration. It's only when I finish this loop or pause the loop, to be more precise. I'll start with column j, start looking at the integer indices and decide, oh, I need to call recursively, and so I'll keep track of that p-value right here. So the recursive stack is now initialized. And you notice, by the way, I'm using the name for the matrix as G, not L. No big deal, no big difference. The reason will become clear shortly as to why I'm calling it G, not L, because I'm going to use this for more than a lower triangular solve. So the recursion then first looks at the top of the stack. Okay. And we have some initializations to do, so forget this line again, because this j new is just equal to j. We have some initializations to do. When you first come to a node, you need to know when that happens. When you first come to a node, you're going to start the column pointer, the iteration, the for loop, from it's going to start at, and it's easier to go back to the previous slide. The first time you see a node, you will mark it. It's not yet marked. Then you have to do p equals lp of j. So starting a node marks it and grabs the initial value of p. So when you're on the recursion stack, you pull off the j from the stack. You've got to know, well, is this coming back from the recursive call of its children, or is this the initial visit of this node? And the distinction between those two is whether or not the node is marked yet. If this node is not yet marked, then I've got to mark it and I've got to do this initialization. If it's already marked, then it means I'm continuing where I left off. So that's what this next test is then. Here, if it's not marked, then I've got to mark it and put onto the p stack G of P, or L of P. And that's what this ugly thing is. Okay, ew. I've got to and it's ugly for two reasons. First of all, it's the matrix might not be complete yet. But for the moment, I'm telling you I'm going to ignore that, but I keep mentioning it. But right here, we've got to get that column pointer. But remember, we're also using those column pointers to mark the nodes. And we don't want, at this point, the mark. We don't want a negative column pointer. We've got to take the absolute value, if you will. And so we've got to call the absolute value on GP of new, unflip it, unnegate it, remove that extra little sign bit. Okay. And then we can now we can decide, okay, that's where. And now we put the p-value here. Okay, now that we've started this node off. Okay, so then we've got to figure out where to terminate. So this doesn't have to go on the stack, but the loop always terminates at the same place, at the end of the column. And so now we start at the p stack of head. So this might have been just initialized, or it might be already there. So we start there, and we finish at this point p2. p2 is just a temporary scalar to make this line fit on a single line. If I wanted to be extremely parsimonious with, minimize the number of semicolons in the code, I could have just taken this right here and stuck it there, but that'd be extremely hard to read. It's already bad enough. So this is my for loop that's going to iterate across the column. It starts at either the starting point or where it left off. Okay, it's going to always finish at the end of the column. So what does it need to do then? It needs to look at the node, and if it's marked, it needs to do the DFS. If it's unmarked, I'm sorry, I got that backwards. If it's marked, it needs just to skip it. So if this node is marked, we just continue on to the next iteration. So it just loops around to the next one. If it's unmarked, we've got to start a new DFS. So to start a new DFS, we've got to redo this work here. We've got to save the position where we are currently. So I go back here and I update this P pointer. So it looks like this. I'm at J. And I've come to a node I that I need to visit. Okay. And I want to come back to here when I finish, which I suppose I could have put in P++ there, but I don't. I just saved this position here on the P stack. So there's my position P, and that's where I want to pick up where I left off at this position. Really, I could have stored P+1 and I would pick up here, but the code was already getting complicated. I was trying to keep it concise. Because I'll look at this and I'll see it's marked anyway. So I'm going to I need to save this position so I can come back to it. And start the recursion for this guy. So to start for the recursion for this guy, the node I has to be pushed on the stack. And P will be placed there later. The P for that would be placed here when I loop around. So save the position where this loop is, push onto the stack the node I, set a flag saying, look, we're exiting this loop, but there's really two ways of exiting this loop, right? You can terminate here, which means that node J is done. So that's the flag done being true here. So if done is still true, then this loop terminated by the finishing of this column. If done is 0, that means this loop terminated in the middle, and then we're to come back to it. We're not done yet. No matter what happens, whether the loop is done or not, we've got I on the stack. Well, no, if it finishes this way, I'm sorry, there's no I on the stack. I take that back. In fact, that was the simplification I could have implemented as I was thinking just this morning, looking at this code. There's an easy way to determining how this loop finishes, but let me wrap up what I'm doing here. So the loop finishes either by terminating on this condition or by breaking out of the loop here by the fact that we've pushed something onto the stack. We've got to start a new iteration. If we did break out of the loop here, if this condition becomes true, then we finished column J. In which case, done is still true. In the if done, then now we need to do the finish work on J. J has finished. There's no recursion to start. So we need to pop it from the stack because it's no longer needed on the stack. We've finished it. And we need to push it. So there's a pop here, decrement the head pointer, and then push it onto the output stack. So then J goes here. It's removed from here. So if it looked like this, if this was our stack here, and then we had a J here in some P value previously, and we say, okay, oh, hey, we just finished J. So J is popped off of here and pushed onto here. And it is possible, of course, for head and top to be equal, but that's fine. J doesn't move, just the head and tail pointers move, which is safe. And that's it. Now, the observation I had this morning was that I could have removed this variable done here completely, I think about this. And I could have had a more elaborate condition here to determine whether or not I'm finished. In particular, if this condition holds, if I leave the loop this way, then the top of the stack differs from j. Whatever it is, it's I, but it's not j. J is no longer at the top of the stack. If I finish this method through this route, j is on the top of the stack. So I could have checked here, is j on the top of the stack or not? If j is on the top of the stack, then I'm finished with j. And that would have deleted 2 lines of this code. The setting of done here and done there, I would have deleted that variable. And then I could have just put a little test here that says if j is equal to xi of head. That changed this assignment into an equality test and put it there. I might try that and see if it works. It should work. All these little observations. That would have cut 2 lines out of the code. It'd fit better on the slide.
There's a couple different ways. You could also compare P to P2.
Yeah, I could have compared P to P2, right? If P is equal to P2, I could have done it that way. Let's see. Yeah, I could have done it that way. That'd actually be better. That would be faster because P and P2 are going to be register variables probably because they're internal scalars, whereas this is the head is a memory, possibly a memory reference, so that would actually be faster. So if P is equal to P2, then I would know that I'm done. That would probably be a better test, because then it'd be more obvious as to what I'm doing. Because if P is equal to P2, you could look at this and say, oh, that means the loop finished. Whereas if top of the stack is J, whoa, that's a little more vague. So I like that better, actually. Thank you. I'll try that. Project 2.1. So that's the recursive algorithm written non-recursively. If you've never taken a recursive code and written the non-recursive version of it, it's an interesting exercise. It's non-trivial. It's mechanical in one way. But anyway, so where are we? We're all looping all the way back here. This is still our algorithm. We've computed the reach of B. So we've computed the non-zero results. Well, now we just have to do the triangular solve. So that's what the next code does. It puts this all together. It calls that recursive algorithm, non-recursive implementation of a recursive algorithm, to do the DFS. Then it iterates through those results and does the triangular solve. Okay. But here, it's going to look a little different. So I come in with, this is a sparse triangular solve, and I call it G because, in fact, it's going to also work for our upper triangular matrices as well. And that's the interesting thing, is that a depth-first search of a graph doesn't really care what the node numbers are. All it cares, all we know, all we can guarantee, not all we can guarantee, is that, but we can guarantee that if the graph has no cycles, if you have a directed acyclic graph, and you do a DFS on it, you get the nodes out in topological order, whatever that order is. In other words, it's an order that preserves the direction of the edges. Well, now think about an upper triangular solve, which we haven't looked at all. This graph, if this non-zero represents an edge from, let's see, if this is uij, if uij represents an edge from j to I, then this graph is also a directed acyclic graph. and a depth first search on this will also produce a topological order. And in an upper triangular solve, I already derived this, but one way of writing it is, well, let's suppose we store the thing by column. And what I showed was that we could visit the columns in this order from right to left. And see if I remember. You first do a division. Let's see. Let's go back to the U solve. Here's the U solve. Yeah, we first do a division for the upper triangular solve, then traverse over all the non-diagonal entries and do this work. Okay. Take X, take the row index, and decrement it times the Uij times X. Okay. Now compare this with this. What happened here? We first do a division, and then we visit all the off-diagonal entries and do the same scatter-gather. Oh my goodness. Wait. That's the same code. I mean, I wish I would have put it, so here it would just jump out at you. Because this is different code between these two, unfortunately. But this is from the LX, this is the L solve. This code is the same as this code with two differences. The loop iteration is different, but that's just because the topological order would be in a different direction. This is one topological ordering of all the nodes of the graph, from n minus 1 to 0. You start with the division, you iterate across everybody else. So from L solve to U solve, the only difference is the order in which you touch the nodes. But the order in which you visit the nodes, if that's a topological order, then that's already taken care of. Then the other thing that differs is, well, where is the diagonal entry? Is it at the bottom of the vector or the top of the vector? Right here, it's UP of j plus 1 minus 1. Whoops. And here, it's at the top of the column. That's the only thing that differs, is where the diagonal is. And if we had a matrix which was stored in such a way that it was assumed to be unit diagonal, all the diagonal entries were 1 and they weren't stored, then we could just delete this line of code completely. Because you don't need to do the division and the entry doesn't have to be stored. If that were the case, the L solve and the U solve would be absolutely identical except for the order in which the for loop happens. They would be perfectly identical. But you see, with the DFS, it's going to do that ordering for us. And so the code would be unrecognizably not different. Or so. It'd be completely the same whether you want to do upper triangular solve or lower triangular solve. You pass in the graph, and the algorithm doesn't care. And it's not. There's no impact on the algorithm as to what it's doing. It doesn't need to know what it's doing. It's doing a lower triangular solve, upper triangular solve. All it's doing is solving a system of equations which is represented as a directed acyclic graph. And in fact, in that case, if we don't even worry about where the diagonal is, if we don't even care about the diagonal, we could have any matrix whose DAG would be, whose graph would be a DAG. Obviously, you can have, if you have a system of equations that looks like this, a 2 by 2 matrix looks like this, it's not a DAG. It has a cycle in it. In which case, we can't use this algorithm. This algorithm only works if the graph is a DAG. But if you have any graph that's a DAG, whether it's upper triangular, lower triangular, or anything else in the middle, right? Just as long as it's a DAG, this algorithm would work. So my code is not quite that general because I have to know where the diagonal entry is to do the division. So here's the sparse triangular solve, putting it all together. And the cool thing is that this algorithm can do two things. It can solve the problem when the matrix is lower triangular or when it's upper triangular. So if it's lower triangular, the only difference is I have to pass in a flag that says, well, where lower or up? You know, this is true in the case of a lower triangular solve. So the first thing that happens is we find the reach. So that's the CS reach function that I just spent almost the whole hour explaining. Okay. Then I assume I'm being passed in a workspace, X, the numerical workspace, where I'm going to do all the work, which is uninitialized. Because I've been using it for other stuff. It's just a garbage array of the right size. So, but I have to set it, I have to clear the array. So to clear it, I don't want to clear the whole thing. I just want to go through and clear the parts of it I'm going to use, which is this piece right here. Any other part of X will be unused and untouched. So that happens first, and the next thing that happens is the scatter of X. This is the statement X equals B in the pseudocode. This is the scatter. And then there's the loop. That's the 4J loop in the version that doesn't exploit the sparsity. It's either going in some topological order across the nodes of the graph. I get out the thing and ignore the capital J because that's the inverse thing that I'm going to have to come back to later. Now I do the division. Okay, and the division is affected by whether it's upper or lower triangular because it's where the diagonal is. So is the diagonal at the first part or the last part of the column? And this loop here has to differ because where's the rest of the entries? Is the rest of the entries all but the first one or all but the last one? And that's what P and Q are. Okay, so this has to differ as well. So this upper-lower thing only affects where the diagonal entry is stored. If I chose to use instead a data structure in which, say, the off-diagonal entries were stored in this graph structure, but the diagonal entries were stored, say, in a dense vector, okay, then this code would be much simpler. I could just grab the diagonal, divide, and then go through the off-diagonal entries. And that's it. There's the loop inside, and we're done. And I have to return the top of stack here because the output of this algorithm is two things. It's the numerical values, which are stored in this work vector X of size n, and it's scattered. So suppose X is non-zero in positions 5, 10, and 17. Then the double precision vector would look like this, where the rest of the data here is garbage, literally. It could be anything. It's uninitialized and untouched memory. So it's anyone's guess as to what it is. Whatever it was on input is what it is on output. I haven't touched that part. But if 5, 10, and 17 are non-zero, then what's going to happen is the output stack, which I've erased, I guess I could use this one. The output stack will have in it 5, 10, and 17. Or, that's assuming, say, I did a lower triangular solve. If I did an upper triangular solve, it'd probably be reversed. Right? Because 17 would probably appear before, suppose it looked like this. 17 and 10, and there was a non-zero here, then 17 has to appear before 10. Suppose this was my matrix. Okay, then if I did a forward solve on if this is on U, then the topological sort would produce 17 first, and then 10 would finish, and then 5 would finish. So the stack would be the opposite. No, wait. I'm sorry. 5 would finish first. I got that backwards. If it was an upper triangular solve, 5 would finish first, and then 10 would finish, and then 17 would finish. No matter which node you saw first. 5 would always finish first. Right? That'd probably be useful to refresh this. Let's how a DFS works. So suppose I've got a graph. that looks like that. My claim is that the topological sort will always produce this no matter which node you visit first. Suppose the input is also, B is also 5, 10, and 17. So in fact, there's really nothing to do. But we need to prove that. So suppose you happen to start at 10 first. See, B itself does not have to be sorted. This is the key observation. B itself does not have to be a sorted column index. Suppose we start at 10. If we start a DFS on 10, because we're going to do a DFS starting at 5, 10, and 17. Suppose we happen to choose 10 first. If you do 10 first, you won't see 17. You'll first start at 10. You'll say, well, who do I have to reach? Who can I reach? Oh, I can reach 5. I'll do 5, and then, oh, I can't reach anybody. 5 finishes. When 5 finishes, it goes on the stack. You come back to 10. You say, oh, nobody left. 10 finishes. And then you iterate to the next thing in B. Whether it's 5 or 17, doesn't matter. If you see 5, well, you've already done that already. If you see 17, oh, here's 17, and then look at its neighbors. They've already been marked, and you push 17. So if you start at 10, that's the output. If you start at 17, that's the output. If you start at 5, that's the output. Doesn't matter. That's the beauty of the DFS. It always produces a topological order. It may produce a different topological order, but this graph here only has one. Okay. If I were to take this edge out, well then 5 and 10 could be reversed in the topological order. And I could produce either one depending on how I visit the graph. But either one is valid. I don't care. As long as I satisfy the numerical dependencies, I don't care what order I do it in. So that's why this code then works transparently for the upper triangular case as well as for the lower triangular case, just with this little extra low flag that says, well, is it upper or is it lower? And since it was a very simple thing to add, and I thought, well, gee, let's make this code a little bit more usable, upper and lower. So the code has to return two things then. It returns this list in topological order of the output, and then it returns the scattered form here. And so now if you want this in a compressed sparse column form, you've got to just do the gather. And that's left to the caller, to the parent, not to this function. Because what are you gathering into? It depends on what you want to do with the result. This is out of order, and this is where this code would now at this point would differ from MATLAB. MATLAB would have to, if the result was for MATLAB, then MATLAB would have to do the following. MATLAB would have to do a quick sort on this column before it could return that result, which would add an extra logarithmic time complexity, which they have to do. That's life. Actually, they don't even use this algorithm. If all you're doing is this, x equals L/B, they don't use this method at all. They know about this method. This method is actually in MATLAB. But they can't use it for here. It is used internally in the LU factorization and other places. But think about what has to happen here. When you do L/B, you might use the letter L in your MATLAB code. But MATLAB does not know that it's lower triangular. It doesn't know. It could be upper triangular. It could be any matrix. It could be rectangular. It could be anything at all. MATLAB has the backslash has a meta algorithm that says, well, let's see, is it upper triangular? Is it lower triangular? The test to see whether it is lower triangular has to visit the whole graph anyway. At that point, there's really no point in exploiting this algorithm at all. You've already spent the work to touch every node at every edge in the graph. So when you do this in MATLAB, you use none of what I've just shown you, because it doesn't know. This algorithm works only if you know that you have a graph that's a DAG. But what if you didn't know that? You'd have to look at the matrix and say, oh, look, it's lower triangular. So now, the test for determining if it's lower triangular is very simple. MATLAB has sorted arrays. You look through the matrix and you decide, oh, look, The first entry in the first column is in the first position, and then the second position, the third, the fourth, all the way down. Upper triangular is the same way. You can do the similar test. You can look at the bottom element. And oh, you're on the diagonal. The bottom element's on the diagonal. The bottom element is on the diagonal. The bottom element is on the diagonal. If that's true for the whole matrix, it's upper triangular. So in either case, you can have one pass over the matrix. In linear time, order n time, you determine, hey, the matrix is upper or lower triangular. But look what you've just done. You spent order n time to do that. But all of this work that we've done, all of this theory, oh my goodness, all this work, was just to get rid of that n. That's all we did to the past, last class and this class. All we've done is gotten rid of this n in this asymptotic time complexity. That was it. But you take this time just to determine that you can use this algorithm, well, then it's pointless. You might as well just use the basic algorithm and just use this one on the screen right here, because you're going to have to spend the linear time anyway. Okay, so that's the lower triangular solve. That's chapter 3, and then we'll start chapter 4 next class. See you then. And I'll be in my office if you have questions on the project. Until 11, not after. See you then.